actually do a live demonstration, but this will suffice for now. So, is everyone in the screen share? Does everyone know how to join the screen share? Should I take that as a yes?
I think most people.
Yeah, we're good.
That's good to hear. Okay. Yes, welcome, Killer Whale, my homie. Math department life, I feel. It's always good. I mean, this talk is, yeah, the workshop's being recorded. So, all right, let's get started then. So, welcome everyone to Introduction to Machine Learning with Neural Networks by me. Well, not fully by me, but let's take a look at what we'll be going over tonight. So we're going to start with Grant Sanderson's deep learning series. In case you don't know who Grant Sanderson is, he runs the YouTube channel 3 Blue 1 Brown, which makes great educational math videos. So we're going to watch his entire deep learning series. That's going to take about an hour. So basically what this is going to cover is first the introduction to what a neural network is. For those of you who have absolutely no experience with machine learning whatsoever, you're going to find that the neural network is a concept that runs through all of machine learning, and it's also very prevalent in end game AI and whatnot. And then we're going to go over gradient descent, which is the process by which neural networks learn. There's going to be a bit of calculus, but we're going to kind of skirt the calculus just a little bit. Don't be intimidated if you don't know any calculus. I know as computer science students, we're expected to take, and I mean, even if you're not a computer science student, I imagine you've taken a bit of calculus. So then we're going to go over what backpropagation really does, and backpropagation is the process by which the network actually learns. The gradient descent is basically, all of this is essentially just teaching the network how to learn features and whatnot. And finally, we're going to go over the calculus. This video is like 10 minutes long. You're 100% permitted to sleep through this because it's kind of hard and intimidating if you don't know Calc 3. But otherwise, it's a really good resource. And then we're going to take a look at the actual code that they've provided for us from these videos. And this code is going to be very math-based. This is just going to use NumPy features. So if you don't know so the code's going to be in Python. Python is a very readable language. So even if you don't know Python, I feel confident that I can explain all of it to you. But so long story short, this code just uses NumPy. If you know what that means, it's basically just, they're basically doing all of the raw math themselves in the code. So it's impressive, but it's kind of hard to read and hard to look at unless you've completely followed along with all of the math. Then we're going to actually jump into machine learning frameworks, which is much, much easier and nicer to look at. And it's really, the reason we're doing this is because I want to show everyone that machine learning, even if you don't have a strong grasp on the backpropagation calculus, you can still use these technologies very effectively to write classifiers in various languages. So we're going to be using Tensorflow, which is Google's machine learning platform for that. And the first thing I'm going to do is we're actually going to compare the code that they wrote using pure math with the framework code. And then after that, we're going to show a convolutional neural network. I'm not actually going to explain how convolutional neural networks work. If you want to learn that, go take the AI class. It's they give a very good, concise overview. All you have to know is that it's better at classifying images than the neural network we're going to see. And then finally, at the end, if we have time and we're not running too much overtime, I'll go over a bit of my own research on classifying different data types using convolutional neural networks. So let's jump right into it. So we're going to go watch 3 Blue 1 Brown's neural network series. This will take about an hour, and we should be getting to the actual examples around 9 o'clock. So I highly recommend you watch this series. This is one of the best series on neural networks and deep learning. Can everyone hear this? Can I get a yes, yay,
Yes,
nay?
I can hear it.
Yes? Okay, that's what I like to hear. Okay.
Can I turn it up a little bit louder?
Can I turn this up louder? How loud is louder? I don't think I have any more dials to
This is
turn.
a 3.
Is that loud enough?
Not really.
Not at all, actually.
Oh god. I
There's
don't
a
have any
volume
other.
slider in the stream for everyone. You can change there. I don't know. Check if that's at the max volume.
Yeah, check if my personal volume is at max. Make sure that that's at max on your end, because everything on my end is max volume right now. Actually, let me check my user settings, voice and video. Nope, that's all set. I'm at max volume.
Try it now.
It's sloppily written and
How's that?
It's good for me.
Actually, it doesn't work for me, actually.
On max volume, I'm okay, but I can't speak for everybody.
I can hear James well, but not the video. Like, it's mumbling a lot.
Well, they haven't said anything yet.
I mean, like, they said something like before you turned back.
You try it out for like a couple seconds, and we'll see how it is again.
Let me try decreasing the frame rate to 720p of the stream, and we'll see if that fixes things. Stream settings, stream quality. I'm gonna go down to 30 FPS at 720p.
this is a 3.
How's this?
It's sloppily written and
Better?
rendered at an extremely low resolution.
No.
20.
Robin, I don't know what to tell you. Does anyone else want to try streaming it? Just see if it fixes it for Robin?
I think some people are going to have the same problem as me.
Yeah, if you are having this problem, please let us know. No,
I think
just
someone typed.
June, are you having this problem too? I will turn subtitles.
I mean, we
on
could
for
use a
everyone.
different, like we could use different software to stream it, like Rabbit. But
Rabbit
Discord doesn't work.
Rabbit no longer exists.
Wait, no way.
Rabbit's been gone for like 3 years.
Dude,
They rebranded, and it's like an entirely new application.
I'm out of touch.
I guess we're doing it
Well,
like,
we're at a bit of an impasse unless anyone else wants to offer up their streaming services to us.
I mean, I could try to play the video on my end.
Yes, please make an attempt. We will.
Okay.
I'll send you the playlist link right now. That, or we could all watch it ourselves. Hello, CZ.
You can go to settings and then voice settings. It'll make it much more clearer.
Voice and video settings. What setting?
No, just
though?
voice.
Alternatively, we could use like watch together.
I think that's
No,
the new
put
Rabbit.
Voice. No, put voice setting and stream volume.
Where do I find that? What's the?
It's on my iPhone, so I'm not sure.
Wait, can you link it, James? Let me see if I can stream it.
I linked it already. It's in workshop text.
Here, one second. I'll try sharing mine, and then we'll see.
All right, yeah, try yours first, Matt.
Okay.
Make sure you share window and not screen. If you share application, not screen. If you share screen, it doesn't do the video. I mean the audio.
Yeah. So, I gotta leave this. Stream. So I'm watching. All right.
I can't believe Rabbit doesn't exist. Holy shit.
Yes, very surprising. I know.
What happened?
I think they rebranded, and I think they're watched together now. I'm not entirely sure. Play. Let's hear some noise.
Yeah.
I don't hear.
I don't hear it. I don't hear it.
Okay, let me try something quick. One second. Here, let me try something. Here, let's try now.
Oh,
This is a 3. It's sloppily written.
kind of
at an
scuffed.
extremely low resolution.
It sounds like I'm listening through someone else's speakers.
Yeah.
Was it better on mine?
Yeah, it was way better than yours.
All right. In that case, I think. I mean,
just put subtitle, I think.
Connor, do you want to try and set up watch together, or whoever
Let me try
proposed
this
that?
Is my mic on? Yeah, I'll do it.
All right. Connor, you make a last ditch attempt to set up a watch together.
Create your room. Okay.
What are we trying now?
1 sec.
Which I think is the new rap. I'm pretty sure.
What was wrong with the name Rabbit, dude?
All right, I trust all of you. Here, I'm gonna put this in the workshop text. Everyone, just join this, and then James, paste the link of the video in the chat, or send it to me or something.
It's already in workshop text.
Got it.
Oh, sorry.
Oh god.
That's the playlist. I'll click this. Ay caramba.
Oh boy, I got an advertisement for Blender.
I got one for
Nice.
Blender. Yeah.
Oh, we
Blender.
got.
If I do this,
Oh, yep.
Oh, looks promising.
Garlic.
Oh,
Yeah.
looks promising.
three.
Sounds
did it.
good. High
did it,
quality
Reddit.
volume.
I think we got it.
I think we're set. All right, so good work,
Is
Connor.
everyone in here?
You've saved the day. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many people we got in this room? 1, 2, 3, 4, 5, 6,
14.
7, 8, 9. We're missing 3 people who are probably AFK right now. But that's fine.
it happens.
It happens.
Always.
All right.
Always.
I might be the only one who can control it.
It's
so.
sloppily written and
Nope,
rendered at
looks like I
Okay.
can control it too.
Okay,
low
cool.
resolution
That's
of
good.
28
I
by
trust all of
28
you. Don't.
pixels.
I think we can all
Has no
control
trouble
it.
recognizing it
That's
as
fine.
a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this,
All right,
this,
so
and this are also
everyone,
recognizable as 3s, even though
Let me pause it for a sec. So we're gonna watch this video, and then we will go on to the next one, and then there's 3 of them. Okay, I just want to make sure we're all on the same page here. Also, it looks like we got more people in the room, which is great.
Excellent.
Okay, so we'll start for real now. I'm sorry for the hold up, everyone. That was not that was unforeseen, and we will attempt to take this into consideration for future workshops.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is... This is a 3.
Why would you do
It's
this?
sloppily written.
Did someone just reset?
Why would you do this? Who reset the video? Connor, is there a way to take permissions away from people?
There is, but I've never done it, so maybe this right here. Enable
Click on-
moderation.
Please do that.
Is it because someone here joined randomly? Everyone here is green
I
names
think
except one.
so.
Can you make the room private?
Oh dear.
Damn.
Unless you've been living...
I was really into it.
Yeah,
I was enjoying.
I know, right?
Activations in one lane.
I was like crazy.
I think you can see who's doing stuff in the bottom corner. We just have no way to stop it. Alright, wait. Can everyone... I think we can change our own names. So if we all change our names to who we are, then we'll be able to see what we're actually doing.
Who the hell? Someone changed the background?
What is going on?
All right, everyone, change your names, I guess.
Stupid question. How do you change your name?
Okay, I just figured it out. In the bottom where it shows like all the people, you find you. Yours is the one with the underline, and you click it, and then it asks you to type in a name.
The problem
nice.
is, can we make the room private?
I don't know.
I feel like the next solution would be just to watch it on our own computers and pause whatever, but that's a little...
That gets sketchy. Okay, we actually have like random people in here.
Wait,
Connor.
I mean, can I try and stream it? We'll see if it works.
Was moderate.
I can't figure out how to change my name.
It's the underline.
No, wait. If Carolyn is the last person in here, then I think we're good.
Well, no, we got a white name in here.
There's 3 people, I think, that are...
I'm trying to change my number.
Do we want to try Discord again?
I mean, that also works.
there we
Everyone
go.
who's you can watch my screen
Yeah,
while
that's
we watch the thing.
There we go.
So for everyone whose audio works, just watch it on my screen.
Okay, I think that's
Unfortunately, there's
the
no
move.
way to... How do I... Oh, yeah, yep, that's what I'm talking about. That's nice. Okay. In that case, why don't we...
Yeah, I'll just watch yours.
Alright.
Okay, fair enough.
Please...
Yeah, me too.
Please do not press any button. Thank you.
Yeah.
I will... No one control except me. Thanks.
Wait, are we going
Just
back?
watch it on YouTube, James.
Yeah, just watch it on YouTube.
Like directly through YouTube.
That also works.
Yes. So we're back. We're basically back to where we started.
Yes.
It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number. Specifically, a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels, the hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be, And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then, the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer, And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector, and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos.
Hello, everybody. What did you think of the first video? Does everyone have a decent grasp on the general theory that we've gone over so far?
is pretty cool.
That's what I like to hear. That's what I
How
like
was
to
it,
hear.
though?
I have
So-
a question quick.
Yeah. Ask any questions on this part right now because it only ramps up from here. This was pretty straightforward overall, but yeah. Ask what.
So the sigmoid function, is that just really using like the data that you have from those points or from the I guess I forget the name nodes, I guess, but like you put them in a vector and then you're multiplying it. Is that really classified more or less as a nonlinear transformation of space?
Yeah, sigmoids are nonlinear functions. That is 100% correct. And the reason we're putting it into the sigmoid function, if I can actually find the area here where they go over that, is because when we add all of this up, we want our like these. This is the exact frame I wanted, right? Because when you add up all of the activations of the previous layer with the weights that are coming in on the tendrils between each layer, and you add all of that up, that could be like a massive number or a super negative number. But what we want to do with the sigmoid, the goal of the sigmoid, is to shrink that onto 1 and 0, because the activation of a single neuron can only be between 1 and 0. We want to limit it to that, because otherwise things could grow out of control. So what we do is we use the sigmoid function to basically make it so anything that's very negative is very close to 0, and anything that's very positive is very close to 1. And then everything else, you get a nice like little slope in between. And there's actually a whole theory of activation functions. This is just one that happens to work. But there's another very popular activation function called the ReLU. Let me grab the ReLU activation function. Not videos, I want images. So the ReLU activation function is actually just x equals y, and it's straight up. And this is another very popular one for machine learning, especially on some more complex. I mean, people often compare them, right? You see here you have the sigmoid, but basically the goal of both of these is to squish in between 0 and 1, right? Because you want your network to only have activations in between 0 and 1. So
could you kind of see that closer, kind of corresponding to like how would you use like the modular or the modulus function to kind of keep a number within a range if it's very large?
Yeah, I mean, you could think of it like that if you wanted, except in that case, then you're like looping around and going to the other side, which we wouldn't want to do in this case.
Yeah, that's fair.
We want to understand. But yeah, it's the same concept that we want to limit the range of our output in between 0 and 1, and we're using this function to do it. And yes, you can use, theoretically could use modulus, but it not would not recommend that in this instance, since it would mess things up. But yeah,
I think it's kind of similar.
So any other questions about this? The core takeaway from this whole thing is that we are using we're taking this is basically the feed forward pass. We're putting all of our activations in, and we are basically we have these weights, which you can think of as, plus and minus values on every single pixel if you want, whether or not we should activate more if we see that or activate less if we see that. And then we have our activations, which are from the previous layer. And then we sigmoid on that to just put this value in between 0 and 1. And then we have the bias.
But maybe it's once in some other number.
The bias is just the thing on the end that basically, for every single neuron, we just want to know, basically this is the threshold at which we should activate, if you want to think of it like that. So that's the core idea of this feed forward pass. Does anyone have any other questions about this? Because this is probably the most important thing in this entire video. If you understand this concept, that our weights and biases are how much we want a pixel, our weights are how much we want a pixel, and then the sigmoid squishes that, and then the bias is our activation threshold. If you understand that, we're golden to move on. So does everyone, any questions left? I mean, this is a hard topic. Don't be embarrassed if you have questions.
I was just going to ask if biases are usually that arbitrarily picked. Like, is it calculated?
Yeah, the biases are learned by the network, essentially.
Okay.
So we're going to get into how they actually learn the biases in the next video.
All right, cool. That's what I was thinking.
We're going to move on then to part 2.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of two hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kinda like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is, and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are, And the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller, and that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with two inputs and one output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with 2 inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us 2 things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with 2 variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable. That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. Alright, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that. It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Now, if you play around with the hidden layer structure and make a couple tweaks, you can get this up to 98%. And that's pretty good. It's not the best. You can certainly get better performance by getting more sophisticated than this plain vanilla network. But given how daunting the initial task is, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Originally, the way that I motivated this structure was by describing a hope that we might have. That the second layer might pick up on little edges, that the third layer would piece together those edges to recognize loops and longer lines, and that those might be pieced together to recognize digits. So, is this what our network is actually doing? Well, for this one at least, not at all. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly. But instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined, unmoving digits centered in a tiny grid, and its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, that'll only happen if you engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now and think deeply for a moment about what changes you might make to this system and how it perceives images if you wanted it to better pick up on things like edges and patterns. But better than that, to actually engage with the material, I highly recommend the book by Michael Nielsen on deep learning.
Hello, everybody. Welcome back. I hope you all found the second video interesting. Does anyone have any questions, comments? Personally, I always think it's very funny when he goes over the part where he shows that the network is actually completely random and that it's found a local minimum in the 13,000 dimension input space rather than actually, doing what he proposed it would do in the original video. Any questions before we move on? This was certainly complicated. I find it hard to imagine you all perfectly understood it.
I'm pretending I understand it.
This is kind of not a weird question. I just want to figure out how to phrase it. So the, I guess, series of stages that it goes through, how does it take the cost function? Like, I know, is the cost function something that comes out after it makes its initial guess, or is it something that is generated?
So this would cause confusion. So he never actually explicitly went over how we get the cost function. All he says is the cost function exists and we're able to use the cost function. And in the next video, he's going to actually go over how we get the cost function. But this has been, so essentially, we actually go look at what the cost function is and the definition he had on it.
One more quick question about the cost function. Just quickly.
Yeah.
So when it finds, like, as it goes through the whole thing of backpropagation, does it exclude some part of the cost function, or is it able to kind of minimize what it's looking at after that, like, I guess, bad turnout?
Yeah, so rephrase the question. Wait, say that again. I need to hear that again.
So say I'm looking at the total cost function, right? And my neural network outputs just a totally terrible answer. And it kind of has maybe some kind of record or, of that path. Does it look at now, since it's been told that that path was bad, a smaller subset of the function?
No, it's essentially the function. It's trying to minimize the function in 13,000 dimensions using the gradient vector. So it's not looking at a subset. It's just getting closer and closer to what it considers the minimum weights and biases. But the way we actually set those weights and biases, we'll see in the next video.
Okay, thanks.
Any other questions? So as we can see, the cost function here, it takes all of our weights and biases as an input. It outputs how bad those weights and biases are, and the actual parameters that go into this are all of the training data that we have shoved through. And it's very important, especially in the beginning. He kind of goes over how we're supposed to do this, right? So we get the minced training data collection, and then what we actually end up doing with those is, let's see if I can find the actual spot in it. But we can, I think this is it.
It's never seen.
So essentially what you do is you split up your data to have a training set and a testing set. And you want to make sure that they're separate because you want to give it things it's never seen before to test on, to make sure that you've actually learned it after you've trained it. And the training is actually setting the weights and biases, while the testing is trying to figure out how well it's performing after you've set the weights and biases. And we'll see that in my examples afterwards. All right, so any more questions before we move on? I know it's intimidating material, and especially some of the more mathy stuff. But if not, no, we will move on. Episode 3. I think we're going to skip episode 4.
Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last 2 videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weight connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to this second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow, so instead you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having.
Hello everybody, welcome back. I hope you found the third video interesting. Are there any questions? Concerns? Things you want to point out? I know this was probably the hardest video out of all three of them. We're gonna skip the fourth video because that goes into some heavy calculus that, I mean, how does anyone want to go watch the fourth video? It's 10 minutes.
I'll watch it.
Does anyone else want to watch it, or would you rather I get into the code? Vote
Well,
now,
actually,
workshop
if you want to
text.
get into the code, then that's probably better.
Yeah, it's I will go into the code just a little bit. We're gonna look at some of the code here that we've been using so far. So this was the code that he showed off in the video. Let's go to a simple thing. So the evaluate. So we saw this in the the first section, or the first video, where essentially you're just feeding forward through the entire thing. Where's the sigmoid in here? There should be a sigmoid in evaluate. Or is he actually just... Oh no, he's actually running feed forward. Okay, I see. Where's feed forward? SGD, feed forward. Here's the actual sigmoid, right? So essentially you have your biases and your weights, and you are essentially just computing the forward pass for a single layer. That's what this looks like anyway. Okay, yeah, so he's looping through every single layer, I think. Yes? Self.weights and self.biases are... I assume the weights and biases are layered, like these are arrays of the weights and biases for each thing. And that's why he's able to do... Yeah, so this is actually... They're working on matrices and arrays here. This that's what the weight matrix for a layer. That's why he's zipping it, and he's doing a for loop through all of them. So this is probably the easiest thing to read in here. This is the stochastic gradient descent function. We're going to skip that. The backpropagation algorithm, we can see basically all that's going on for the backwards propagation algorithm is we are quite literally, genuinely, moving forward or backwards through the network as this goes on, right? So I would love to read all of this and actually delve more into this code, but I imagine people are probably sleeping at this point. So if that's the case, I think we should move forward into some of the the easier code with TensorFlow, which I'm very happy that I will be able to give, hopefully, a decent overview of how much easier this is and take a weight off of your shoulders after seeing that brutal calculus and linear algebra heavy code, right? So let's move on into... I see something in workshop text. Could you see what the hard... Did I not show what the hard code looked like? Did everyone see my GitHub? The GitHub I was sharing? So this is the hard code, essentially. So yes, they're purely using NumPy to do the entire... They are actually doing the math for all of it themselves. In modern day, we do not need to do any of this math ourselves. The libraries handle all of this for us. So they can... yeah, it's not that big. Like, this is a reasonable amount of code. Like, it's 141 lines, and most of that is comments. So it's not actually that bad. You would just have to read through how... there's a lot here, though, still, right? So, like, the update mini batch, like, this is... Update mini batch is when you update the network's weights and biases by applying, a single gradient descent with backpropagation for a single mini batch, which, if you understood the third video, you understand what that means. Where you split up all of your training data into mini batches, and then you're doing a backwards pass based on a single mini batch. And let's see, where are they actually doing the computation in here for the backpropagation? I should see it in here. Are they not? Oh yeah, here it is, self.backprop. Okay, so they're computing the... Okay, that makes sense. And then, of course, the backprop is the hardest thing to, follow along with. But we're going to completely ignore that for now. And what's really great about TensorFlow, I'm going to switch over to TensorFlow, and you guys are going to think that this is a joke about how easy this is to do. So this is that entire network in 40 lines, and it's much, much nicer. So let's talk about what's actually going on here. So the first thing we're running is... okay, well, first I should probably explain what TensorFlow is. So TensorFlow is it's written in C and C++, but it's Google's machine learning library, essentially. And there is a package built on top of TensorFlow called Keras. And Keras is... I think it's pronounced... It's either Keras or Keras. Keras, I don't know. But essentially what it is it contains all of the it contains really simple ways to build models and everything, which I'll show you in just a second. And when I refer to a model, I'm referring to, like the physical manifestation of the picture of the neural network that you see in the thumbnail and everything, right? Like the when you Google neural network, what do we get? Yeah, like this is a model, right? We have layers in the model. I hope you followed through that, but essentially, it's not that bad at all to actually generate a model. So can everyone see this? I'm gonna zoom in anyway. Oh, and let us, okay. So let's actually take a look at what we have here. So the first thing I'm doing is I'm disabling TensorFlow warning messages because TensorFlow decides to.
Am I the only one who can't see the stream?
No, I can't see it either. I was about to say.
Oh, that's right. Okay, well that
Yeah,
explains
it's
why.
paused.
It's the fact that I shared on
The window, right?
window for the video. Yeah, I forgot to switch it over so I could look at. I'm out here like going over all of the code. All right, hang on. Let me fix this real quick. Screen 1. Okay. Can everyone see my screen? VS Code.
Yes.
Yeah.
Okay. Love to hear it. So I was ranting about Keras before, when you guys didn't see anything about Keras. But okay, so basically, this code is like 39 lines. I don't know where I just lost a line. But anyway, so let's start at the top and just go through. So quick survey. Who knows Python? If you don't know Python and you know any programming language, you should be able to follow along what Python looks like.
Yeah, Python is very human readable.
Python is crazy human readable. There's some weird quirks though, right? Like Python functions can return multiple values and whatnot.
I
So
would say it's not a traditional programming language if you think of traditional programming languages.
yes, it's really not. So let me discuss the broad high level overview of what you do for a machine learning program with TensorFlow and Keras. So the first thing you do is you set up all of your training data. And then after you set up all of your training data, you create your model, which is the actual network that has all of the nodes and layers in it. And then finally what you do is you start talking about all of the batch size and how long you're going to train it for. Then you compile your model and then you train it. This model.fit function is actually just meant to train it. And then I save it to a file so I can use it later. But then essentially this model evaluate, this is what's running it on the tests rather than the training data. So as I stated before, you have to split it up into testing data and training data. But before we really get into that, let's actually go through line by line from the top. And hopefully everyone will understand everything that's going on. So first we import OS and we do OS environ, this flag right here. And all this does is say, TensorFlow, please disable your warning messages, please, because they're insanely annoying. You get like 100 warning messages when you try and compile this program. TensorFlow outputs just right when you input, or right when you import, they will hit you with like 100 warning messages about how they can't detect your GPU and everything. It's like, I want to use my GPU. I just want to run the program without all of these warning messages. So that's what those first two lines do, import OS and OS environ. That's setting an environmental variable on your system. But after that, we're importing NumPy. So NumPy is the most popular scientific computing Python library. It's a linear algebra library that makes linear algebra really simple, and it's very fast. So you get matrices, vectors, and lots of different operations you can perform on those, right? So then TensorFlow is the actual TensorFlow library, which is Google's machine learning library. And that includes support for like hundreds of things, but primarily what we're concerned with is the fact that it has support for tensors, which tensors are just multi-dimensional matrices, basically. So imagine, if you know what a matrix is, and you picture a matrix as a square, the simplest example I can give of a tensor is a cube. And then you can even get like 4-dimensional cubes and higher dimensional cubes. And that's a tensor. And we don't really have to worry about like what it's doing with tensors behind the scenes. Just know that in machine learning and artificial intelligence, you're working with a lot of tensors. I mean, we got the feel for that from those videos, right? We're in a 13,000 dimension space. So it should make sense that we have some very high dimensional data that we need to work with. And the perfect tool mathematically for working with that data is these tensors. So that's the core idea right there. And there's even more stuff later on about that. But for now, just know TensorFlow. That's why they call it TensorFlow, because tensors, higher dimensional matrices, vectors, So then next we import Keras. And now what Keras makes writing models in TensorFlow 100 times easier. And it looks very nice, and I will go over that. And it also has some utilities. So the layers are the actual things that we use to build the models. That's why we're doing TensorFlow, Keras, layers. And then Keras is just for the utilities, basically. So the first thing we're going to specify, so we're actually going to design the exact network that 3 Blue 1 Brown just used in that video to classify the MNIST handwritten digit data set, right? So the first thing we want to talk about is the number of classes. So when we talk about classes, we're not talking about actual classes and object-oriented programming. We're talking about the number of possible outputs of the network. So what can a handwritten digit be, right? We have 10 classes. Those classes are the digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And yeah, so that's 10 digits, including 0, right? So then we want to specify the input shape. So in Python, this is called a tuple. And a tuple is basically an ordered, it's kind of like an array. You can think of it as like a constant array where you can't change the values, well, once they're set. There's probably some more fancy stuff about tuples that I don't personally know. I think can you have multiple different data types in tuples? I think that might be what differentiates it. I think you can do that with arrays in Python too. So it's, anyway, just think of the tuple as an array. So what we're specifying the shape of the tuple. So when we talk about shape in Python, and especially NumPy and TensorFlow, what we're talking about is the actual dimensions of this object. And when I say object, I mean array. So we're basically saying that you can visualize this as a cube that's 28 by 28 by 1. And by 1, I mean, you could just think of it as a square then, basically, right? 28 by 28 square. So what is that shape? That's the image that we're putting in, right? That's the actual image that's coming in. And I've actually created a nice little test model here. I'm going to actually show you what one of these looks like. And this will make more sense in a second, but I will, let's pause it right here. And as you can see, TensorFlow loves to take a long time. So this is actually a 5, this right here. So this is the first image in the data set that we can see right here. So this is a 28 by 28 square of pixels, basically. And the reason that our input shape is 28 by 28 is because these are actually grayscale images. They only range from, I believe in the video, he did 0 to 1. I still have them on 0 to 255. Because it's another line of code to, get them down between 0 and 1. But long story short, that's why the input shape is 28 by 28. Everything makes sense so far, right? I haven't gone over that much, right? This is pretty straightforward. The input shape is the shape of our image, basically. The number of classes is the number of outputs we have. And all of the imports, everyone understands why all this is here. So let's go over the next line then, right? So this line is, this is a very Pythonic line, right? Because we're basically declaring these 4 variables in one line from this function right here. So this keras.datasets.mnist.load_data, what this is actually doing is loading in all of the training data. So the MNIST database is so common and prevalent that we don't actually even have to import a file or anything ourselves. Keras comes with this built into it, which, I mean, that's kind of a bloated library feature, but you know what? I'm using it, and it's very convenient. So what this load data function actually does is it loads the MNIST dataset into these variables right here. So basically, remember back in the video, he said that you have to split up your training and your testing data. So that's exactly what we're doing here. We have our training images, our training labels, our testing images, and our testing labels. Now, I don't know if you remember why the labels are so important, right? So the reason we want the labels is because at the end, we need to evaluate the performance of our network. And the only way to do that is with the labels to tell us what the actual value of that image coming in is. And we're going to be able to use that to detect what the, what its output, and then we're going to be able to use the labels to perform backpropagation and gradient descent. But we're not actually ever going to have to touch that. TensorFlow is going to do that, all of that for us, and it's going to be glorious. So does everyone understand this line right here? Any questions on this? I know this Pythonic syntax. We're basically just, it's outputting tuples. So then we're declaring these, this is like declarations. We're not actually declaring these tuples, it's outputting tuples, and we're putting our values in, and we're declaring these as the output of the Keras function, or the Keras load data function. Does everyone follow so far? Yes?
When you call that the keras.datasets.amnist.load data, how many tuples is it spitting out, I guess you could say?
So that's a good question. What's the format of this? So what's interesting is the training images is actually a massive cube or a massive like rectangle of training images. So the actual format of this is all of these images are loaded into one array. And we can actually find this by doing, I'll do it over here. And nope, that's not the one I wanted. Where is it? Test model. I can actually get the shape of these. So if I do print training images dot shape, and I will pause right there, we'll see that the actual shape of this is like a massive slice, basically. Let's see, did it print? Yeah, so the shape of our training image data is 60,000 by 28 by 28. And what that means is that basically we have this giant rectangle, and each slice of that rectangle is it's like a rectangular prism. It's just like, a three-dimensional rectangle where the width and height are the actual images, and then like the entire, whatever the x dimension is, whatever I can say, length is like you're going through all of them. So each one of these it's like a massive array. And in Python, the way that we actually access this is through these slice operators. So what we're saying here when we say plot, match, show training images, we're saying take the first, you can just think of this as like an array of images if you want. It's probably easier to think of it as an array of 28 by 28 images rather than like a giant rectangle like it actually is. But what we're saying here is we're saying take the first thing in that rectangle and then get the 28 by 28. And this is returning the image of size 28 by 28 because these are open-ended slice operators, which just mean take everything. And this is returning a 28 by 28 matrix, which is our first image. Python can get really confusing with slice operators, but as long as you have a basic grasp on what it's actually representing, it's fairly straightforward. Any more questions on this? So the labels, actually, it's just a single vector, or a single array, right? The labels, this is an array of 60,000 training images, and this is an array of 60,000 just numbers. And each number in this training labels corresponds to what the actual image represents. And it's the exact same thing with the test images and test labels, except the test images is smaller because we're testing on a smaller set than we're training on. You want to train on a larger set than you test on. So any questions about this? Does everyone understand that we are splitting it up? This is images, and this is just numbers of what the images represent, the real values. No questions? We good? Okay. In that case, I will move on to this. So this Keras utils to categorical train labels, num classes. What this actually does is, let's hover over it and see. It converts a class vector of integrals to a binary class matrix. I have no idea what this means, but I'm 100% sure that you need this. I'm pretty sure what this does is that, let's see. See, I have an idea of what this does, but I'm too afraid to say it and be completely wrong. So I'm going to ignore these lines for now. I'm pretty sure what this is doing is it's taking the labels and it's reformatting them to make sure they're like the same format as the number. Like, imagine you had like text labels and it wasn't just straight numbers. It needs to like put this into a vector at the end, or an array at the end, so it can figure it out. And I'm pretty sure what this is doing is it's converting our class vector to, to a binary class matrix. Yeah, okay, I was right. That's exactly what it's doing. So it's basically converting whatever our label set is to a numerical label set. So in the end, once it's done, we can actually figure out what it's converted to. So then next up, this is really cool. So this is the actual how you build models in Keras. So when we have a model in Keras, all we have to do is specify what layers we want in our model. And when I say what layers we want in our model, I literally mean like what slices down our model. We can pick and choose like how many nodes do we want in this slice, how many nodes do we want in this slice, and that's exactly what I'm doing here. So for the first layer, I'm going to ignore that for now. I'll explain that in a second. But let's take a look at this first. So I'm saying for the first layer, we have 16. And then for the second layer, we have 16. And then for this final layer, we have num classes, which is 10. So this is the exact network that they use in the 3 blue 1 brown video. If I pull that up. Nope, that's the wrong one. Where's like the real one he was using? Yeah, this one. So we have 10 nodes in the output layer. We have 16 here. We have 16 here. And then we have this flatten layer right here, which is actually the one that has all 784 nodes at the start. So what the reason we have a flatten layer here is there's actually a hidden layer that he's not showing here. Because somehow we have to convert this image that's in a 28 by 28 form into this 784 long vector. So that's what the flatten layer is actually doing. It's basically just saying, let's take this 28 by 28 and just flatten it down into a single 784 long vector, right? So that's what this flatten layer does. But you can see like it corresponds line for line with the network in the video. We are quite literally, let's see if I can go over here. We have our first layer here, 784. We have a 16 layer, and we have a 16 layer, and we have a 10 layer. So let's talk about what's actually in here. So for this Keras input right here, this just basically tells you what the shape that you're inputting is. And for us, it's the input shape, which is the 28 by 28 image, right? And then that's getting flattened, and then we're running it through a dense layer. We're running it through another dense layer. And then finally, we are outputting into this num classes layer, which is 10 long. And this is what we're actually going to use to classify things. So you can also see that we're using activation sigmoid. So you can specify for each layer what you want your activation function to be. So for us, it's the sigmoid function, as we saw in that video. That he was using the sigmoid function, which is squishing everything down. But sometimes you might actually want to use a different activation function depending on what you're doing. And I'm going to show that off in the next example. So this model so does everyone understand the model right now before I go into it? Keras.sequential is just what you use to build the model. Some networks aren't sequential. Some more advanced networks have layers where it's like nodes will randomly connect in between different layers, skip over layers, and it will randomly not connect some nodes. But for our purposes, Keras.sequential is just saying to build a sequential model. And a sequential model is just connect every node in this layer to every node in the next layer, like the way that we've specified here, using these dense layers. The dense layer is literally just a normal layer that has every single connection go through. Does this make sense? Does everyone understand what's going on here?
So for each sequential layer, are you applying that whatever, I guess not, or transformation like sigmoid you're doing? I thought that was at the end.
No, so sigmoid happens on every single activation for every single node. If we reference back to what's actually going on, because we want to make sure every node's activation is in between 0 and 1. And that's the purpose of the sigmoid. is that we really want to get it down to, I think it's right here. We really want to make sure that, so for every single node in a dense layer, we have to run this computation on to get what the output of this node is going to be, the quote unquote activation of this node. So as you can see here, we're coming in with 784. We are running this big summation is happening on 784 waits and activations of this first layer. And then this could be some massive number. And then we're applying our sigmoid just to figure out, okay, so what's it going to be on like this node? What's our activation going to be, so we can keep it nice and clean in between 0 and 1.
Okay.
So that's the purpose of the sigmoid function, but of course we don't actually have to use the sigmoid function. We can use whatever we want. But for our purpose, we're recreating the exact network he made, so we're using sigmoid for now. And we're going to see that this isn't actually the best model, but it is pretty good. So any other questions before we move on to the next part? Everyone good with this? I feel like this is probably a lot easier to understand than the, actual hard hitting stuff. And I know I'm sorry, I wanted to get some live coding, but it was probably too much to ask everyone to figure out how to install TensorFlow. It's actually not as simple as just installing a Python library in this case. It kind of is, but at the same time, it's kind of not. So there's maybe if there's interest, we can do stuff at side project development night tomorrow. But for now, I'm just going to keep going through this live code walkthrough. I hope that's okay with everyone. So anyway, let's talk about this next part. So we've created our model, right? Which everyone gets this. It's literally the model we had in the video. So after we've actually created our model, we're going to do model summary. So I'm actually going to pause here and show you what a model summary looks like in TensorFlow. So it's going to print it out for me right here once it's done. All right, excellent. So in TensorFlow, this is a very common thing that you use, is your model summary. So what your model summary does is it actually prints out what your model looks like. It will tell you your shape and the number of parameters. So basically what we're talking about here is it literally just, it should display exactly what we've shown, right? So we have the flatten layer, which takes our image and flattens it, and it has 784 nodes and 0 parameters. And that makes sense, right? Because if we see on here, these nodes on the input layer, they don't have a bias and they don't have a weight because it's the input layer. Nothing is coming into these nodes. So it would make sense that there are no trainable parameters on this first flatten layer. So then we're going to look at this dense layer, and we can see that this is where things really start heating up. And this is where all the parameters, the weights and biases are. It's because this is where we're actually connecting 784 times 16 weights and plus, I think it's going to be, 16 biases. So that's where we're getting this number from. And then, so that's our first dense layer. Then we have our second dense layer here, which is another 16 long. And that's, now we're connecting 16 times 16. And that's, I feel like I'm doing these calculations wrong. Now that would make sense. And then we have to add the biases as well, and that would be 272. And then finally, for our last dense layer, we're connecting this 16 to our 10 and 170 trainable parameters, right? So in total for our network, we have 13,002 trainable parameters. And yeah, so all of our parameters are trainable. And some networks, you get non-trainable parameters, but we're not going to have to worry about that right now because that's for more complicated networks. This is just the bare bones basic neural network. Everyone understand this so far? I basically just reiterated what I said in the Keras version, but with model.summary. So next, let's talk about the batch size. So as they were saying before, when we perform stochastic gradient descent in the video, they were discussing this. We want to split up our training data into little batches. We don't want to do them all at once. We want to make sure it all gets split up, and this will make it much faster to train than performing the gradient descent analysis on every single training example and then looking for the right direction. We're just going to perform it on 128, then take a step, and then take another step. And then essentially what these epochs are is how many times we go. So they didn't mention this in the video, but an epoch is every time you go over all of your training data. So we're basically going over all 60,000 images in step sizes of 128 20 times. And each time the network is going to get better and better. That's why we're doing 20 epochs. We don't actually have to do 20. Let's do, for now, I think that's a big number. So let's do it 5 times. So does everyone understand batch size and epochs before I move on? This makes sense. We split up all 60,000 of our training images into one batches of size 128, and then we go over all of that data, and then we do that 5 times. That's what the epochs is. Everyone understands this. We good?
So could you consider the epoch kind of just like a loop variable almost?
Yeah, almost. Your network is getting better and better every single time you loop over that data. That's the core idea of the epochs. So next up, if there's no other questions, last chance, you can ask anytime. But so next up, we're going to compile the model. So you don't see this in the pure math version, but basically what TensorFlow does when it compiles the model is it wants to optimize the model, basically. The same way when you compile your C++ program, it's converting it over into assembly to make it super fast. TensorFlow is going to compile your model here and turn it into a super fast network. So what you actually have to pass in is an optimizer, and I actually have no idea what the optimizer is. I've never touched this parameter, but I always leave it Atom by default. I think that's what their just default optimizer is. So then the loss, this is interesting because you can actually do, you can play with your loss function. So what your loss function is at the end of, after you go through and you've backpropagated through everything, I believe it's in chapter 2 actually here. Let me scroll through real quick. It's the mean squared error, where you're adding up all of your results and basically comparing with what you want and trying to figure out, well, what the heck did I do wrong? So MSE stands for mean squared error, but there's lots of other different ways you can compute the loss rather than just mean squared error. So that's our current function for at least, because we're trying to model exactly the network that he built. So we're going to be using mean squared error to, actually compute. So then finally, what we have here, so yeah, we're trying to get the best accuracy, but some people also want to compute for lowest loss, but we're not going to do that because loss is kind of meaningless to us. We just want highest accuracy. So any questions about compilation before I move on to fit? Fit is going to be the last thing I have to go over, basically. So model.fit, this is probably the most interesting thing. This takes all of the complicated backpropagation math, all of the calculus, and crams into one function that you don't even have to care about. And it just does it automatically for you. This model.fit will literally try and optimize your function, or try and optimize your network, and optimize your model to get the highest accuracy at classifying images when you do a feed-forward pass. So this does all of the backpropagation for you. All, like the last 3 videos in that series, it's all handled by this one TensorFlow function. And this is like the majority of the code in their massive code base. This does it all for you. You pass in your training images, you pass in your training labels, you pass in the batch size, the epochs, and don't worry about the validation split. We're going to ignore that for now. And it just does it. It just computes it, and it just gets you the highest possible. It tries to minimize the cost, negative cost function. No, it tries to minimize the actual cost function. Yes. So that's what this does. It basically goes through all of your batches and epochs and minimizes. Right. So then what you can do is once you fit the model, you have the weights and biases of that model, and you can just save that to a file and load that up whenever you want. So you only have to train your model once, and once it's trained once, you can just pull it out whenever you want and use it to, classify images or classify handwritten digits in a completely separate project. So that's what makes this that's what makes machine learning so cool, is the fact that it's you can really, once you have those weights and biases, you can just save them and load them back up later. And I'll show you guys an example of that after this. But I think that's super cool. So finally, what we're going to do is model.evaluate. So this is going to use our test data. And the test data is, if you remember up here, the test data is the stuff that wasn't in the original data set that we've kind of excluded because we want to use it to try and train, to run the model on later on and actually figure out, like, well, how much did we actually lose on going through all of the image, like after we've trained it to be as good as possible, how much do we actually lose still? So that's what this model evaluate does, and this returns a score. So the first, it returns an array. The score is an array, and the first number is our loss, and we're not going to worry about our loss. This basically just tells us how much we lost while training. So like how bad were we during training, and then finally our accuracy at actually modeling, like basically getting the basically what percentage of numbers did we classify correctly. And this is super cool because you're actually able to see, okay, out of these 60,000, we got like 80% of the numbers classified correctly. So let's actually run this now. So, well, before I run it, does anyone have any questions on these last few lines? The model.fit, model.save, model.evaluate.
What does score encompass completely? Like, I know you're using the indices there. Like, how many? Is it just those two?
So I think score might actually be bigger. Let's actually take a look at what it returns. So it returns the loss value and metrics value for the model in test mode. Let's actually see what that encompasses. I've never used anything other than just 0 and 1. Returns scalar test loss if the model has a single output and no metrics, or a list of scalars output metrics. Okay. It will, oh my god, it's really complicated. You can get the metrics underscore name. I mean, I can output that. We can take a look at what we have available. I'll do that at the end here. Print. Actually, I think I can do that right after the summary.
Might as well check it out.
Metrics underscore name, I believe. Print that. Yeah, let's see what else is available. Sure. Okay, so let's compile this and check it out. So it's the first thing it's going to do is it's going to print it out. Of course, TensorFlow takes forever to load up. Oh, great! It doesn't have any metrics to evaluate. Maybe I have to do it after the fact. Let me move this down here. After it's been fit, let's just print it out before the actual metrics. Let's see if this actually works. So now we are actually training, and as you can see, we'll look back at this later, but we have essentially, okay, it did not print out the metrics, but let's actually take a look at it. This is cool, right? So for our first epoch, I don't know why it's 422. I still don't fully understand where it gets these numbers from. It's supposed to do every single, I never specify an epoch size, but it kind of seems to randomly choose those. Anyway, regardless of that, so what this is here is the loading bar, and it tells you how long it took, and then it tells you how long it took per step, and then it tells you our loss, and then it tells you our accuracy for this epoch. So I don't actually, why is val accuracy versus, I'm not entirely sure what the val accuracy versus the val loss is, but let's just focus on normal loss and normal accuracy for now. So what this is actually telling us is during the first epoch, during these first training examples, our accuracy is 0.22. That means we successfully classified during the first epoch, by the end of it, 22% of images correctly. We were correctly able to guess what the handwritten digit was 22% of the time. And you can see as the epochs go up, we get better and better. So during the second epoch, we managed to classify 31% correctly. During the fourth epoch, or the third epoch, 48, and just up and up. Until finally the fifth epoch, we managed to classify 67% of images correctly. And by the end here, so keep in mind that the test data is not at all related to the training data. So despite the fact that we only had 67% accuracy on our training data, it turns out that when we actually run the test on it, our test accuracy is 70%. So we've made the it was actually a bit better than what was realized here in the fifth epoch's test accuracy. Where for the real test accuracy, we're getting 70%. So if we boost up our epochs, let's boost up to 20 right now. We're going to see that it actually levels off around like 93%. This model can't really get better than 93%. So if you give it a hot second right here to actually train itself, And you can see we're getting up in the high 80s right now. Our final accuracy is 88%. I've gotten, so this is entirely possibly due to the fact that we just had, bad starting conditions, and that's why it's not in the 90s. I was hoping, you can see it really kind of levels off at 88 here, especially during these last few epochs. And that's kind of the problem with these basic networks, is the fact that you can get really good results, but you can't get perfect results. You're always going to have like 10% of results that we can't classify correctly with these more basic networks. And it just fails to learn these simple things. So if we actually take a look at, so Matt, to answer your earlier question, it looks like when I do model metric names and I print those out, we only have loss and accuracy available in this array. So that's interesting. I did wonder if there was anything else, but it doesn't look like it. So any questions about training and this model before I move on and show you guys some more cool stuff? I'm also going to try and I'd like to try and classify my own handwritten image, which isn't going to go well. I can hear it now failing, but I will take a look.
I have a question about the I know in his video Grant said that I think the maximum amount of this model couldn't classify depending on the epochs was like 98, did he say?
I think he said 97.
97. So yeah. So that being said, theoretically, because I don't want the epoch, like I was gonna say, as the epochs, go incredibly large, near infinity. That's theoretically, because of course.
I mean, see, the other thing is, I'm not using his. He never told us what his batch parameter was. I never got what the batch parameter was, and I'm not entirely sure if MSE does the exact same thing that I think it does. I'm pretty sure MSE is the right loss function here, but and also the model.compile is using this Atom optimizer, and it's behind the scenes. This is doing like some black magic that I don't even want to think about what it's doing.
Yeah.
And of course, we also have like the validation split parameter. So there's like, he never had anything like this with his basic model. So there's definitely a few more parameters we could tweak to see if we could get anywhere better. Like, what if let's do 500 batch size, and let's see if we do 5 trials, if that gives us better performance. I don't mind taking a look. Epoch 1 out of 5. Oh, it's taking a bit longer. Great, only 43%. That made it worse.
Yeah, isn't the batch size how much you're splitting it up? Like
the higher batch size, the larger. Yeah, so let's try a smaller batch size. Let's try, what was it before? 128.
Yeah.
Okay, in that case, let's bring it down to 50. Oh, I think I understand what that is. That's the so if it's the steps, that's okay. I get it now. So now we're doing. Oh, accuracy is already looking much better. 84 after 5. Let's try 20 epochs. Sure, let's go for it. I think this is bad. Just wait until we get to convolutional neural networks. It's going to take like a minute to train each epoch. Yeah. This is surprisingly comfy.
I was gonna say too. I know he brings up the term stochastic batch size, or what was it? Stochastic something.
Stochastic gradient descent. This is stochastic gradient descent.
Okay.
Otherwise, you would be doing batch sizes of like 1.
Okay. So, is it reaching like a steady state like vector that it? Because I know that involves like matrix multiplication and whatnot.
It's reaching a local minimum of the negative cost gradient, basically.
I guess, yeah, I was just trying to say, like, taking account, like, this model can only be, at its best, like, 97% efficient, and it doesn't matter what you do, I guess, it stays that way at its maximum, you know what I mean?
Yeah.
Like, so I'm guessing it's just approaching, like, a steady state no matter what you do, I guess was my
you can think of it as the ball rolling down a hill problem. You can reach the bottom of the hill, but once you're at the bottom of the hill, I mean, sure, there's lots more hills and lots more trenches, but the ball randomly rolled down your trench, and now it's at the bottom, and the only way to, retry that is, you see every time I rerun the network, even with the same parameters, it's still randomly initializing the weights and biases to randomly roll down a different hill every time I run it. So if I ran this like 500 times with different weights and biases, maybe I would get that 97% hill. We really just don't know. So that's one of the that's kind of how this works. So that's the general idea, is that you're basically just rolling down the cost function into a local minimum, and then it kind of just bottoms out. Like as you can see here, and I mean, it's not like once you get to the bottom, you're still able to move like a little bit further down, because you have to keep in mind that we are in a 13,000 dimensional space. So you're going to be able to get like a little bit lower, but you can tell when you've bottomed out and things start to just stay the same. So, okay. Next, in that case, any more questions about this, the model building and saving things and everything? Because otherwise, I'm going to go take a look at this, which is actually pretty cool. So this file right here is to test the model. So as you might recall, I actually saved my model, 3B1B model.hdf5. HDF5 is just a neural network weights and biases storing format, and you can use that for anything TensorFlow generates. So once you have that, you can move that to another computer, you can share that over the internet, and you can give someone your hard-trained network, and they can basically use it to simply classify digits in really fast time. So what we're actually going to do here is we're going to work on single digits. So, and just kind of show what's going on here. So what I'm actually doing here, this file is pretty straightforward, right? I'm loading the Keras data set, same thing as last time. I'm going to remove this line to print the shape that I added in, just to show you what the shape was before. And then I'm actually using matplot or pyplot. What's it called? Pyplot, yeah, so pyplot, we are going to show so I'm using matShow, which just show matrix, basically. So this is, and we're saying use the 28 by 28 image. So that's why before it was displaying that 5. And you're actually going to see, this is pretty funny, it thinks that this 5 is a 3 on the one that we just trained. Well, actually, it might not anymore, because I've just retrained it like 5 times. What was our final percentage, actually? Because that is actually, I think it was like 87. We should be fine. But before, when I was playing around with this, it was going to it almost always classified this 5 as a 3. But I'll show you later on that it actually fixes that in the more advanced method. So basically, I'm just loading the model in. I'm training it. And then as you might remember from the 3 blue 1 brown video, that final vector at the very end is basically we take the highest thing from that as what we think our value is. So let's actually run this. And we're going to see that, please tell me I'm not loading CNN. Okay, no, I'm not. So we show, yes, please show me it. So this is our image, this is our 5. And now let's actually take a look at what's going on here. So I shouldn't have these pause things in here. All right, so let's see what it actually said. Oh, so yeah, look, it said I'm 74% sure, basically, that this is, we're not actually using softmax, but essentially since this is the largest number, it's saying this is a 5, and pretty sure it's a 5 because look, it's 74. But as you can see, it kind of thinks it's 3 as well. Like 3 is showing some activation here, so it's not entirely sure, but it's pretty sure it's a 5. So that, I thought that was cool, just to see how you feed one thing into the model, and the way you feed something into the model is literally to just treat the model like a function and pass the image in. It's a bit more complicated. You have to kind of expand the dimensions because it wants like a batch size parameter, but these are actually just like empty. So as far as we need to be concerned, we're just passing the image into the model. It's feeding forward through the model, and we're getting this result. And it's a column tensor, but we're just we're exporting that and just saying, going through all of those final 9 neurons, we're saying, oh, so that's what that is. So I did prepare a treat for you guys. I have this 8.png that I drew myself, and I want to try running with this, but unfortunately, when it gets compressed, you're going to see that it's not very good at classifying this, and it's going to be, feel free to laugh at my pathetic attempt to classify my own handwritten digits. So let me comment this out real quick and get my version going. So the image, I have created a special function that converts the image. This is I borrowed this from someone and then threw my own stuff in here at the end. But essentially all this does is this converts the image to a, little vector or a matrix image that can be displayed just like the same format of MNIST images, basically. So let's add those dimensions and let's Just want to make sure I'm running this right. And yeah, so I want to run on model.image. So let's see if we can get it to classify as an 8. I might have to, mess around with the actual image itself a bit just to make this work. Okay, so you can see my 8 here. It gets converted to this. So this doesn't look like other MNIST images. So chances are this will fail. Let's see what it thinks it is. Oh boy, what did it think it is? It is pretty sure it is a 5, which is completely wrong. Wait, is this? Oh, that was the old one. Okay, so let's actually see what it is. What it thinks it is on this one. Did we get anywhere near it? Oh, it was actually pretty unsure, it looks like. Hang on, I just want to... Let's see. Yeah, wow. It had almost no activation, which is actually kind of impressive. I'm surprised it didn't, freak out and think it was something else. But let's actually, if I reveal in File Explorer, see if I can edit. Can I edit this in Paint? I want to edit with Paint 3D. I just want MS Paint. So let's actually just, destroy this entire thing. And let's try this again with even smaller, because I want the lines to be thicker, right? So let's make this as small as we really can, and then get a nice thick brush going, and try and get this to be a nice big 8. It's still kind of small. Let's let's get it even bigger. Yes. Let's see if it recognizes this as an... that's still not that... I want to really make it thick. Come on. Let's do a 5. Why do I feel like this brush gets smaller with me? Am I insane? What if I do a real brush? Oh, that looks much better. Let's do this. Oh yeah, that's what I like to see. All right, let's save this. So we have updated this 8 now, right? Correct? Yes, we have. Okay, let's run this now and check out if we can correctly get this to classify as a 5. Okay, that looks more like a 5. It's still not super big, but we're getting there. And it thinks it is a 4. Great. So as you can see, it's very particular about what it actually gets, right? So let's try this one last time, and if this does not work, I will potentially give up. It really has to be apparently omega thick. I was not expecting this. Let's get rid of you.
Does it depend on the type of like the style of numbers that it was trained on? Like if you drew
think
one?
so. It really looks like it was trained on, because if you look at the entire MNIST database, it's all of the numbers look like these handwritten. They all have like basically the same thickness. They've all been normalized somewhat to have the same like line thickness. And what's screwing it up is the fact that my line thickness is completely off from their line thickness. So let's try this. What if we get a... Oh yeah. Sure. Let's make an attempt. All right. Let's see if we can get him to recognize this guy as a 2. That looks like a 2 to me. Oh, it worked. It's 93% a 2. Glorious. So we have just classified our own handwritten digit, which is very cool. I hope that's what you all came to this workshop to see me blunder classifying a handwritten digit twice and then finally get it on the 3rd attempt. So, I mean, the workshop is now 10:13. I've gone, unfortunately, this is going a bit over time. I think I'm going to skip the part, my research presentation, but I will, to just end things off, I want to show you guys a really cool, different type of network that you'll see a lot, especially if you do any image recognition, which is a convolutional neural network. So the actual setup of a convolutional neural network, you'll see it's very similar to the, get rid of these lines, but it's very similar in setup to the neural network that we just used. And this is more this is like an advanced network that like you actually use for practical applications. I use this in my research for my research purposes all the time. So it's essentially the first like 10 line or 20 lines and 22 lines are exactly the same. We're importing the MNIST database. We're expanding the dimensions. Do I even have to expand the dimensions? I'm just going to ignore that line. I don't think I did that in the other one, but I think I might have to in this one. Anyway, so essentially all we're doing here, if we actually look at the layers, so this is a convolutional neural network. So to give you a good picture of what a convolutional neural network is, I'm going to use my best friend Google to show you what a convolutional neural network looks like. So now instead of layers, we have these cubes of pixels that we're essentially going and performing convolution and then pooling on, essentially, is the idea. And these networks can perform much, much better at image recognition because they're performing convolution and then performing pooling on those convolutions. I'm not actually going to go into how you perform convolution and how you perform pooling because that's a bit beyond the scope of this workshop at 10 p.m. But overall, all you have to know is the fact that these perform much, much better. But they are, unfortunately, a lot harder to train and a lot slower to train. So let's take a look at our convolution network. I'm going to pause it on model summary just so we can get a look at what's actually in it. Essentially, the idea behind convolutional networks is the fact that you're performing these convolutions, these 2D convolutions on the image, and then you basically alternate convolution layers and max pooling layers until your data is a small enough size, and then finally I flatten it here at the end. I use dropout layer, which I'm not even going to go into what a dropout layer is. And then finally we have our good old dense layer that we saw beforehand. And we're going to use softmax, which is going to be greatly beneficial, but I will not explain why. So as you can see here, the shape, we have much more exotic shapes in this network. Our first convolution network is our first convolution layer, it's a cube, a 26 by 26 by 32 cube. And then our max pooling 2D layer essentially divides this in half. It cuts our data down by half, so we're extracting, basically, we've extracted features and we're getting smaller and smaller until you can see by the end we have this 5 by 5 by 64 cube, right? Or it's not even a cube at this point, it's a rectangle, right? Not a cube. But long story short, then our flatten layer, we finally flatten down all of those parameters into the 1600 long neural network, just layer. And then we have a dropout layer, which the dropout layer basically just, I believe the dropout layer, I can't give a good explanation of a dropout layer right now, but essentially this helps prevent overfitting. That's all you need to know, is that this dropout layer, it's a fancy version of a dense layer, but it helps prevent overfitting. Anyway, so then finally our dense layer, we're finally going down to 10 parameters or 10 nodes, which we can use to actually perform the classification. So that was my terrible explanation of a convolutional neural network. You'll have to forgive me. If you're more interested in convolutional neural networks and want a better, more in-depth tour of them, come to the event tomorrow, the side project development night, and I'll be more than happy to go over how convolutional neural networks work. So let's actually start training. So as you can see here, we're actually taking some time to train now, right? So we are waiting on this guy. So we're going to do 3 epochs, but already look at that. We're already up to 82% accuracy and climbing. Once we get up to around 88% accuracy, now we're at 94. So as you can see, we're already way past what the other network was able to perform at. So let's just give it another 15 seconds, give or take, and wow, 95. See how much higher we can get. I've gotten these to around like 98 before, but this is already very impressive. You want to take a look at my CPU graph here? You can see it's really taking a toll right there. There is a GPU-based version, but it's incredibly hard to set up and very annoying. I've tried many times. All right, so take a look at that for our final accuracy. We were able to get 98% accuracy on our tests, which is absolutely insane. Like that's 98 out of 100 images basically classified correctly, when our other one was only able to get around like 88 at max. So we're already performing it by like 10 points. So let's actually take a look at. Let's switch on over to our test model and take a look at. We're gonna stop using the old model. So we saved this model as well. So this is a 98% good recognition model. So we can just load this in and run it right up. So let's see if it correctly classifies 8.png, which now I believe is 2.png. So let's see if how this guy fares recognizing our 2. Let's see if he performs as we hoped and performs well. Okay, yep, that's our 2. Load him in, and it is 99.9% sure that this is a 2, which is a huge step up from our original network. So this is very cool, and the softmax layer means that these values are going to be more accurate in terms of its actual guesses. For like, if you've ever seen a network where it's like I'm like 80% sure that this is a dog, but like 20% sure it's a cat, you have to use a softmax layer at the end rather than a sigmoid layer, which is why in the CNN you see for activation here, I'm using softmax. And then also you might have noticed for our conv2D layers, or is this our conv2D layers, we're using ReLU instead of sigmoid, which is, again, I previously stated you want to use ReLU is actually pretty useful. There's a lot of theory that goes into what activation function to use that I'm not personally up to date with. So if you ask me, well, why are you using ReLU here? Why are you using softmax here? I unfortunately cannot give you a full answer because I'm just a man who uses the networks. I'm not a man who understands the deep theory behind all of these yet. Anyway, I think I hope you guys found this pretty interesting overall. And I would like to. Is there any questions about this? Because otherwise I will move on. No questions? Yes questions? I saw Matt unmute.
This shit is crazy.
I know, it's so cool. I'm in love.
Yeah, it's actually like easy enough to understand using it. It's just like picturing all the stuff that happens in the background.
The math is so hard to understand. I completely understand. It's really easy when you just think of it as the layers. And you listen, like, I like to think Keras sequential. It's literally just like you're putting Legos together, and your Legos are your different layers, and you're just chucking them together. And once you have that, you can apply, as long as you have training data and training labels, you can apply this to any problem you want. Like, this is how self-driving cars work. Like, it's all just variants of this same idea that you're essentially just creating this model and then training it and then running with it. Like, it's great. It's great.
It's cool. I was gonna say, I saw in the CNN the term, because there's a lot of linear algebra little hints. I thought kernel size there, or kernel, which is like the null space, right?
So that is not related. At least I don't think it's related off the top of my head.
Oh, really?
What the kernel size is when you're doing a convolution, those convolution layers, is what you're actually ending up doing is you're basically summing up areas of the image and then taking that sum and throwing it into a multi-channel layer. And that's what the kernel size is actually how many like pixels you're taking and summing up and putting into that new channel spot. So that's what they mean by kernel, is the size of this square, basically.
Oh, okay.
That you're that's what they mean by kernel size. So when it says kernel size here, it's 3 by 3. That means it's taking a 3 by 3 square of pixels from the image and then convoluting them, as in adding them all up, basically, and averaging them, and then just sending it over to this convolution layer. And it's using ReLU as its activation function to be on the convolution, essentially. So that's what the convolution layer does. And then the max pooling layer basically just slices everything in half. I'm still not sure so that's why it's pool size too. Okay, that makes sense. I actually don't think I ever looked at why we use pool size too. But yeah, so that's that. So
I was gonna say one more thing. So for the machine learning and like artificial intelligence classes here, I think it's CS 435 is AI, right? And then I don't know what machine learning is, but do they talk
close to that
about theory, or do they talk about application, or do they talk about both? Like,
so I basically just failed my machine learning or my AI class test today. And no, it's I didn't fail it. It's hard. It's a hard class.
Yeah.
And especially it doesn't help that we're at the end of the semester now, and it's it's all virtual. But it's very theory heavy, and you don't approach it this way at all. You approach it from a much more mathematical perspective, and especially you approach it from a more of a game theoretical perspective in our classes. So you're going over stuff like the first few weeks, like the first month of the class is like search algorithms and like, quote unquote artificial intelligence, like not
Yeah.
real, like, oh, if you're a robot and you want to navigate to a goal, what's the best way to do it? It's like that kind of artificial intelligence. And then like eventually you kind of build in from there to this kind of stuff, but you're never actually really like working on this stuff. It's a lot more theory than it is like actual networks. Like I was hoping to learn the theory behind some of these networks. I get to learn any of the theory behind these networks.
Yeah, because it's just it's challenging. It's just like
I imagine it's above the level that people are working at. And I mean, most people who work with machine learning don't care what's going on behind the scenes. All they care is I have data. I put data into model. Model tells me what data is. Good. That's like that's 90% of what the like when you hear like, oh, I work for a machine learning company, you're not actually doing research on machine learning. You're just basically coming up with these models, throwing your data in, and having it get classified. Like the hype around machine learning is really more, people don't really know what they're doing with machine learning. It's all they know is I can get this to perform, non-trivial problems, classification problems. And that's the real goal of machine learning in modern day and age.
Yeah, I can see it becoming like a more of like a plug and chug thing with that, like kind of like how algebra is with like equations. You know what I mean? Like that kind of a thing.
Yes.
It's kind of a buzz. But it's cool.
It
though.
really is. It really is more of a buzzword at this point than it should be. But I mean, it's a powerful tool, right? Like corporations make great use of this. This is used for targeted advertising. This is used for basically every single thing that you get advertised to you has been run through like gazillions of networks trying to calculate, oh, well, what's going to be the highest cost function if I show him this advertisement?
Yeah.
It's yeah. So that's the kind of stuff that actually goes into this. So any more questions on the technicalities of what we've just done? No? Okay. In that case, I was going to actually go over my own research, which is classifying binary data using convolutional neural networks on processed byte digraph matrices. However, for the sake of the fact that it's 10:30 p.m. and we've been here for 2 hours, I'm going to skip this for now. If you're interested in this, and like if you're really interested in this, come to the meeting tomorrow and ask me about it, and I'm more than happy to tell you about what I'm doing. But otherwise, yeah. So thanks for coming, everyone. I appreciate it. Thank you for staying so late. I hope you all got something out of this. I'd like to apologize for every wrong thing that I've said. I'm not very good at AI yet. I'm still learning it myself. I know I definitely caught myself with a few bad things that I may have said that were false. So also to everyone who, if you're watching this on YouTube, I'm not an expert. Please don't take anything I say too seriously. Yes, I'm just a AI enthusiast like the rest of us. Anyway, yeah, thanks so much for coming, everyone. I hope this was a good resource for you, and good night.